I'm Novakovic from EPFL, and today I'm going to talk about the stable and predictable cloud performance in infrastructure as a service cloud environment. This is joint work with people from EPFL, Nedeljko Vasic and Stanko Novakovic, with my mentor, Professor Dan Kostić from DEA Networks, and Professor Riccardo Benchini from Rutgers University. So last couple of years, we witnessed this great expansion toward the cloud. And the cloud comes with these nice benefits, such as cost reduction, flexibility, scalability, availability, and such. And for sure, a large number of individuals as well as entities have been offloading their workloads to the cloud service providers. And here, for illustration purposes, I'm plotting the ratio between the traditional and cloud-based workloads. According to this study, interesting thing to note is that, for example, starting from the next year, 2014, for the first time, we're going to have more cloud-based workloads than traditional one. According to the same study, by the end of 2016, nearly 2/3 of all workloads will be processed in the cloud. Therefore, it's obvious that we have a pretty high adoption rate. So when we are talking about infrastructure as a service cloud environment, I like this analogy between the IaaS and hotel. So in both cases, we have third-party users that are coming and renting the resources, and they're actually expecting certain value in return. And indeed, it might be the case that VMs are scheduled in a particular way so that users are getting exactly what they paid for. Or it might be the case that due to the fact that underlying virtualization mechanisms do not provide perfect performance isolation, we experience so-called noisy neighbor problem. Noisy neighbor problem, which means that although we correctly configured our application, still we experience performance penalties due to the fact that we are collocated with some noisy neighbor on the shared infrastructure. So this problem with the performance comes from the fact that today cloud users do not have full control over their infrastructure in the cloud compared to their private environment. And cloud is not built for one particular user, it's actually built for millions alike. And while it's general enough to cover some basic needs, it is not specific enough to cover all of them. And today in the cloud, we have a large number of applications running. And those applications share either the same hardware node, they spawn in one rack across the data centers, etc. And things are even worse for the end user, because end users do not have any visibility whatsoever what is happening behind the scene. The only thing that they may notice, and they will notice, is that just suddenly latency, for example, goes up, or that the browser becomes unresponsive, and such. So at that point, I would like to know what are actually performance guarantees today in the cloud. And the fact is that we do not have strong performance guarantees. In order to confirm that, we ran an experiment where we fixed the resource allocation of the key value store Cassandra, and we fixed the input workload, and still over the time, we experienced performance drops even up to 40%. And we are not the only one, because Google in their recent paper actually states that if you collocate certain types of application together, we may experience increased latency. Technology experts keep saying the same. And bottom line here is that we cannot expect always stable cloud performance. To make things even worse, given current technological trend that we are moving toward this many core era, where we can expect hundreds, even if not thousands cores, probability of experiencing interference will just increase over the time. So you may ask, why is this still an open problem? It seems like a basic. Well, it comes with certain challenges, and for sure transparency is really important. And it's really important because of at least two reasons. First one is that today we cannot just rely on the cloud users to report their performance levels, because they may lie for their purely selfish reasons, for example. And second is that today in the cloud, we have a large number of different applications running. And if you're actually to go and to tweak our solution for every single of these applications, our approach just wouldn't scale. Furthermore, interference can be really complex in the nature, because all these applications are actually running in the cloud, and they are sharing same hardware infrastructure, same hardware elements. And these hardware elements also may belong to different hardware generation, may exhibit different performance characteristics, and therefore all this may cause some pretty nasty interference effects. And finally, we would like to have an online approach, which means that cloud operators usually do not have access to the VM prior to deployment. And therefore, it is crucial to have mechanisms to transparently detect and to manage the interference effects in the infrastructure as a service cloud environment. So toward this end, in our lab, we construct the framework that we call deep dive. And the deep dive, in essence, tries to answer the three fundamental questions. First one is, can we reliably and transparently diagnose interference by just solely looking at the low-level metrics? So if we can do that without asking application for input or feedback, we would like to know what is the most dominant source of interference, what is the most dominant cause and component that cause the most of the suffer. So this is so-called diagnosis part. If we know answer to these two questions, we would like to know what should we do in order to eliminate the source of interference and to mitigate the interference effects. And this is so-called treatment. So for the rest of the talk, I will focus on these three questions and briefly explain how deep dive answers every single of them. So main philosophy of the deep dive is to transparently and constantly monitor every VM in order to diagnose and to learn abnormal from normal behavior and to actually mitigate interference effects. So this is the high-level overview of the deep dive. It consists from the three components. First one is the warning system. And the warning system is just a profiler that actually monitors the VMs that we schedule across our data center. And then tries to learn abnormal from normal behavior. And if it suspects something, it will then trigger the next component, which we call the interference analyzer. And then interference analyzer will actually perform more detailed analysis. And in the case that confirms that interference is indeed happening, it will then trigger the third phase, which is so-called placement manager, which will try to come up with a smarter placement decision. So let's now zoom in. In the case of the single hardware node that we have, and let's say that we have a number of the tenants, and these tenants actually submitting their VMs, and these VMs are scheduled in some particular way on that hardware node. So at this point, deep dive diagnosis consists from the two modules that they differ in their accuracy and overhead, namely the warning system and the analyzer. So deep dive first relies on the warning system to perform early interference analysis. And the warning system does that by maintaining so-called repository of the normal interference-free behavior per tenant. And you can imagine this as an n-dimensional space where the n is actually a number of the metrics that we are collecting, where the metrics are, for example, hardware performance counter or system-level metrics that we are collecting. So the warning system is just a profiler hooked up over this single VM, and we are trying to match observed behavior with the already seen interference-free behavior. And if we can do that, then there is no reason to panic because this is already seen behavior and there is no interference. However, it might be the case that these observations actually cluster far away from anything that we saw up to this point. So in this case, we don't know if it's just a workload change or it's indeed interference. So therefore, the warning system here just issued a warning and triggered the next phase, which is the interference analyzer, which will then in parallel construct the sandbox environment from the same hardware type and environment, and will actually migrate the particular VM. So here the intuition is really simple. So we have two same setups, two same hardware components, their hardware environments, and we have two same VMs and same workload and input. So in the absence of interference, these low-level metrics should cluster next to each other. And indeed, that might be the case. So that these metrics are clustering next to each other, and then we're going to know this was just a workload change. So at this point, the interference analyzer will inform the warning system that the last invocation was just a false positive, and that is not interference, just a workload change. And therefore, the warning system will update the repository of the already seen interference-free behavior. So the next time when we see a workload that is same or similar, we will not have to trigger this highly expensive phase. And this is actually one of the ways how we populate this repository. On the other side, however, it might be the case that these metrics cluster far away, again, from anything that we saw up to this point. So this is the actual sign that interference is indeed happening, because we have two same setups and two same VMs and input workloads, and still the outputs are largely different. So this is the way how we actually confirm that interference is indeed happening. So before I say how we actually find the root cause of this interference and mitigate the effect, let me just briefly expand the discussion how we actually populate this repository of the interference-free behavior. So as we saw, one way to do this is to analyzer to notify the warning system and to update this behavior repository in the case of the false positive. However, today usually in the cloud, due to the scale-out nature of the application running in the cloud, one tenant can actually run several VMs. And among these VMs, some of them actually execute in the same code. So if this information is actually known, then Deep Dive can use this global information and further reduce the overhead on invoking analyzer by using the global knowledge and experience from other VMs executing the same code. So once we know that interference is happening, we would like to know what is the cause of interference. And the way how we do that is that by employing the performance model, namely the CPI analysis. CPI stands for cycles per instruction. It's a convenient way actually to show how much useful work machine does and at the same time to point what are the components that cause the most of the stalls. So here I'm presenting one of our experiments that we run on the Hadoop cluster, where we have our CPI breakdown on components, major components of the hardware architectures like core, cache misses, memory bus. And classic CPI analysis does not include network and disk. However, we augmented this traditional CPI stack by looking at the system level metrics and actually expanding it with the network and disk traffic. So what you can see here is on the x-axis we have 3 scenarios. On the y-axis we have stalled cycles per instruction, so lower is better. And here the intuition is again similar. In the absence of interference, these stacks breakdowns should look similarly. However, in the case that we do have interference, the component that causes the most of interference will actually have the biggest relative increase compared to the other components. So in the first case here, we can see that our cache misses are much bigger than all other components. The relative increase are much bigger. In the second case, we are talking about memory bus, and in the third case, actually network and disk cause the most of the stalls. So we evaluated this approach by using different applications. We use various interference levels and types of interference. And finally, we use different hardware architectures to confirm this. So once we know that interference is indeed happening, we would like to know what can we do in order to mitigate interference effects. And one way to do that is just to migrate a particular VM to the alternative destination. And clearly this is policy-dependent, policy-driven. So we may decide to migrate a VM that causes the most of the interference with respect to the particular resource, or we may decide to migrate a VM that suffers the most with respect to the particular hardware component. But in any case, approach we're taking here is actually migrate a particular VM to alternative destination. So one way to do that is that to just speculatively try to migrate VM and to see if that actually works for us. However, this approach makes some time in order to find the right place where we can actually migrate our VM and that our VM is not experience performance penalties anymore. Not only that it may take some time, but also during all this time we actually introducing additional interference because we are running under suboptimal settings during all this period. So what we would like to have is the approach that can quickly, in parallel, investigate the potential destinations and then quickly summarize and suggest the cloud operator what is the best placement for a particular VM. Also, we would like to decrease the state that we are shifting around because usually these VMs come with a lot of state with them. So toward this end, we actually built a novel synthetic benchmark. And this synthetic benchmark is just a set of the loops. And these loops are exercising different physical resources, such as core, memory, CPU, disk, memory, bus, and etc. And by changing the number in these loops, we are actually shifting the pressure from one component to another. So as the input in our synthetic benchmark, we are taking the hardware information about the potential destination that we are considering and that we want to move our VM. And then armed with this information, what we actually do is that we are exhaustively explore this design space of the potential inputs along several axes, such as level of the parallelism, working set size, disk and network traffics, etc. So as end results here, what do we have is that we have ability now to map the low-level behavior observed in the warning system to the set of the inputs in our synthetic benchmark. And although this learning may take some time, several hours in our cases, usually it's done offline of the critical path and once per hardware type that we are considering. So the next time, when we actually have our real information for the VM that we collected during the warning phase, we're going to be able just to quickly react and classify and produce the synthetic representation of the given VM. So this synthetic representation is just a synthetic benchmark model that exercise the physical resources in the same way as original VM. And this is actually the most important characteristic. So at this point, what we can do is just quickly, in parallel, dispatch these synthetic benchmarks and then try to see what is the actual impact on the potential destination. So when we have these results, then we can just quickly summarize and suggest to the cloud operator what should be exactly the point that we should migrate our particular VM. So here, the bottom line is that by using this synthetic benchmark, we eliminate unnecessary migration, and we can quickly in parallel evaluate what is the best placement for our VM that we're considering to move at this point. So let me tell you a bit about our evaluation. We evaluated our approach using representative cloud workloads, namely workloads from the Cloud Suite benchmark published at the ASPLS last year. And here we experimented with 3 applications from this benchmark, namely with data analytics, web search, and data serving. So data serving workload consists of the Cassandra instance that is a distributed key value store. And we experimented with the YCSB benchmark to vary the input instruction mix and key popularity. In the case of the web search engine, we used Notch with 2 GB of the index file. In the case of the data analytics, we use Hadoop cluster running on the 10 machines that we actually trying to perform a modified Bayesian classifier on the Wikipedia data set of the 40 GB. To capture dynamicity of the real world, we actually used the Microsoft Hotmail and Messenger traces from 2009, which represent the aggregate load across thousands of machines and averaged across 1 hour period. And to inject interference, we actually used our observations spotted in the Amazon EC2 experiments, where we were looking in the client reports, and then every drop above 20% we labeled as a performance crisis. So in our experiments, what we did is that actually we used the time slots to inject the same amount of interference as observed in the real world. And furthermore, we used memory, network, and disk stress in our experiments to stress our VMs. Our memory stress benchmark was actually, as input parameter, was take the working set size and then stressing heavily components as a memory controller or last level cache. In the network case, we used the iPerf tool, and as input, we used the desired throughput that we need to achieve. And in this case, we're just copying files with respect to the maximum transfer rate. So now let me just show you a couple of the results. Here in this graph, I'm plotting the deep dive's accuracy. And this is actually detection rate that measures deep dive's consistency in the identifying interference. So here we use the data serving benchmark Cassandra. And here in the blue, I'm presenting the detection rate. And as you can see, it's 100%. So during all our experiments, we are able to detect interference. At the same time here, I'm plotting the false positive rate, which represents the overhead of the running deep dive. So the false positive means that warning system thought that interference is indeed happening and triggered the analyzer. However, after further investigation, analyzer concludes it was just a workload change. And as you can see, during the first day here, we have a substantial number of these false positives. But during the learning nature of the deep dive, at the end of the 3rd day, this false positive rate drops to the nearly 0. So now when you're talking about the overhead of the deep dive, it's interesting to see what are the projections, how many machines we need to use in order to profile in isolation particular VM. So here in this figure, I'm plotting the deep dive's reaction time as a function of the percentages of the VM undergoing interference. So here, as you can see, the intuition is the following, and this graph confirms that if you use the more machines, that will mean that actually we have a lower reaction time. So if we operate in some, for example, let's say region of the 20% of the VMs undergoing interference, and if you are willing to tolerate just slightly above 4 minutes of the reaction time, we would need just the 4 servers to hit the actually high incoming rate that we consider this experiment, that is 1,000 VMs, new VMs coming every day. So these 1,000 incoming VMs every day, this is the worst case, because in this previous experiment we consider it as that every VM is running a different workload. And we cannot reuse the global information that we have. So in this experiment, to see what is the deep dives global knowledge actually, how does it work, we model this recurrence of the 1,000 VMs that are coming as a typical zip distribution, where the few of the tenants actually have a large number of the VMs, and then the rest of the tenants have a smaller number of them with a long tail. And here we actually see that deep dive using the global information can further decrease the number of the necessary servers that are need to profile. In this particular case, it's actually cutting by 50%. So in the same setup as the previous time, we have a reaction time that is just slightly below the 2 minutes. So the bottom line is that our server profiling servers is actually enough in the large-scale environment. And finally, I'd like to show what is actually synthetic benchmark accuracy. And this here figure contrasts the performance loss reported by the real VM and by the synthetic representation. So here on the x-axis, I'm plotting the different working set size in the megabytes, because we use the memory stress benchmark to stress our real VM and its synthetic representation. And as you can see here is that our synthetic benchmark representation closely actually follows the performance loss of the real VM with a high accuracy. So finally, I'd just like to position the deep dive with respect to the similar efforts, because deep dive is actually crossing the boundaries of the several fields. Just mentioned some of the relevant frameworks. So besides the number of the frameworks and large body existing work that considers the performance interference if we have some information about the workload, earlier this year we had 2 papers that actually tackled the problem of the performance interference. And much like global knowledge in the deep dives case, Paragon uses the recommendation system to suggest the better placement decision. CPI2 uses the CPI analysis to determine if interference is happening indeed on chip or not. Also recently we have a number of the synthetic benchmarks that they use in order to determine what is the best placement for a particular VM or application. And in the case, for example, of the bubble up, we have that we are stressing with the memory stress benchmark a particular application to see what is the impact on the collocated application. In the case of the bobtail, we are using the simple scheme in order to determine if particular already running VM is undergoing CPU interference or not. So contrary to these approaches, deep dive is actually making the synthetic benchmark that is synthetic representation of the real VM. We are not actually stressing them in this case. And in the case of the sandbox environment, we have already a large body of work. For example, Just Run It is running experiments in the sandbox environment in order to determine what is the impact of the workload change in the resource allocation, whereas Deja Vu is using similar approach to determine if interference is happening or not by comparing the performance levels in isolation in production. However, contrary to these approaches, deep dive knows exactly what is the reason of the interference and can successfully mitigate the performance degradation. And finally, to conclude, today here I presented the deep dive. And the deep dive is a framework for transparently and efficiently detecting and managing interference. It requires no support for application or the guest operating system. And by employing the novel synthetic benchmark, we can further decrease the overhead introduced by the unnecessary migration of the VM. So at this point, I would like to thank you and be more than happy to take your question.
Hi, Carl Waltzberger. First, I want to say this is really fantastic work. I really enjoyed it. One question I have is around the sandboxing technique that you use, which uses VM cloning. And I was wondering if you could comment on the complexity of dealing with the external interactions of the virtual machine with its environment, say with other machines. I know in prior work you did using application or protocol-specific proxies, and how complicated or how much overhead that adds to the system.
Okay, thanks. It's a great question. It's actually, like you said, it's related to our previous work that we did with the sandbox environment we are using here. So basically what we do is that we actually clone the particular VM in the sandbox environment, and then we use the proxy, which actually intercepts the traffic that is headed to the machine in production, and then dispatches a certain amount of the request to the isolated environment. However, what we have there is also the output proxy as well. So this interaction that particular VM has with other VMs, for example, if we consider the simple three-tier architecture, and the middle tier needs to communicate, for example, with the backend. In that case, what we have is the out proxy, which actually caching the results, the replies of the real VM running in production. And then just in order to introduce the same amount of the load, it replies if that request hits the cache, replies back to the sandbox environment. So at that point, we have that out proxy that take care of the additional dependencies with the other VM.
Can you cope with non-determinism with this, or is that still a problem as it was sort of in just run it?
So in this particular case, non-determinism actually is something that deep dive sees as a noise, because it's usually not so frequent. However, if that is keep repeating over several monitoring epochs, deep dive is actually learn it and label it as interference behavior.
Thank you.
Hey, Ann Holler from VMware. I enjoyed your talk. I had a question about whether there could be a situation where the VM would completely saturate some resource, so it can't play well with any of the other VMs, and it would actually take a two-level move to place it somewhere, like all the trials would fail because all the synthetic placements would fail. And then really the only thing is that if it was by itself, if you could move one of the other VMs in order to place it.
Oh, thanks. So it's a good question. So what we do here is we are providing mechanisms. So our synthetic benchmark will go and explore a particular destination, and then we're going to just rank it with respect what is the best place for the given VM. So it might be the case that VM actually cannot play along with other VMs, and we're going to just see that and report, and then most likely if there are spare and free resources, then the cloud operator will instruct and actually place that particular VM as one solely machine on the particular physical machine.
Hey, Joel Istvan. It's a really nice talk, and the only question I have is I was wondering of this database representation where you kind of use the metrics and then profile the application. I was wondering, do you take into consideration the actual hardware that you're running on? Because I would expect that some of the hardware counters we're looking at can be, or I assume they can be different depending on the actual processor generation that you're using or the hard drive that's attached to it. Because I assume you can have a heterogeneous cloud, right? I mean, you don't have all the same.
Yes, exactly. It's a great question. So for now, what we are doing is that this approach works on the homogeneous set of the machines. However, there is no reason not to apply it on the heterogeneous, because the only thing that we need to take care here is that in this three-level approach, we, for example, use and collect low-level metrics according to a specific hardware architecture. Then we need to have our CPI breakdown also for a specific architecture, and then finally to train our setting benchmark for a specific architecture. So as a matter of fact, we did this because in our original setup experiments, we had one hardware architecture, and then one of our authors, it took him maybe 2 days to port this to another architecture.
Can I just have a second follow-up? Oh, no.
Sorry,
Okay.
I think we're going to have to switch to the next speaker.
Yeah, good job. Thank you.